Hi, welcome to this mini lecture on paleoclimates. In this lecture, I'm going to be going over how scientists can estimate past climates from millions of years ago. First of all, I'm Molly. I'm a paleontology and geology student at the University of Birmingham, and I'm currently in my fourth and final year. I've been doing a placement with Bifor as part of a module in my course, and my goal for that has been to make educational materials like this mini lecture in the hopes to get more young people more excited and interested in climate science. So let's get into it. To understand anything to do with past climates, we first need to get a good grasp on geological time. So geological time goes back in time a really long time to when the Earth was first formed, which was around 4.6 billion years ago. So huge portion of time that we're going to be looking at. This complicated looking figure is called the chronostratigraphic chart, and it basically splits up all of that last 4.6 billion years into smaller, easier to manage sections. And some of these sections should be recognizable to you, like the Jurassic period over here, when the dinosaurs were alive. Today, though, in this lecture, we're just going to be focusing on the last 66 million years ago, right after the non-avian dinosaurs went extinct. And this unit here, MA, just means millions of years ago, so this just means 66 million years ago. Here's a simplified timeline of the last 66 million years. We have present day on the left over here, and then we're going back in time towards the right. So after the asteroid wiped out all of the non-avian dinosaurs, there's a couple of important events in Earth's climate history that we're going to go through on this timeline. The first is around 56 million years ago, and it's called the Paleocene-Eocene thermal maximum, which was a time where the Earth warmed, and it's something that we're going to talk about towards the end of this lecture. Then, around 34 million years ago, ice sheets first properly form on Antarctica, marking a major point of planetary cooling. Then, here in the mid-Miocene, which is around 14 million years ago, ice sheets form in the northern hemisphere as well. At this point, they're only in Greenland, but eventually they stretch down into the UK and North America during the last glacial maximum, which was around, I think it ended around 23,000 years ago, and so that would be around here. Modern humans, or Homo sapiens, didn't evolve until around 300,000 years ago, which is relatively recent in Earth's history. And finally, we've got our most recent event, which is the Industrial Revolution. And this is where humans began to put quite a lot more carbon dioxide into the environment by burning fossil fuels. And since then, atmospheric CO2 levels have increased by quite a lot. So how do we know about these different climate events? Well, there are several naturally occurring climate records, and here are a few of them on this slide. Each of these records a different interval of time, a different length of time. So we first have our tree rings. These are the shortest interval, and they go up to 10,000 years ago, basically just the lifespan of the tree. Then speleothems or stalagmites do longer intervals of 500,000 years. And the stalagmite in this case is just the sticky up thing that you find in the cave. It's not the one at the top, that's the stalactite. The stalagmite is the one that grows from the bottom. And then next we have our ice cores, and these are even longer. They go up to 800,000 years ago. But the real powerful climate record in terms of the time covered and the detail is the ocean sediment cores. And these cores come from the deep ocean, and they can show up to 200 million years of time. For context, 200 million years ago was the very beginning of the Jurassic, when dinosaurs were about. So pretty cool, and a really long period of time to be recording. So to collect ocean cores, a huge team of scientists and a ship crew go out on this boat called the Joydes Resolution. And on this trip out, they drill down into the sediments in the deep sea, like you can see here, and they bring up long tubes containing layers of sediments that descend through time, with the oldest ones being at the bottom. These kind of excursions are part of the International Ocean Discovery Program, or IODP, and I've linked a documentary at the end of this lecture which goes into a bit more detail about what the scientists get up to on this ship. So there are many different ways that we can use climate records to reconstruct past climates. A few of them are listed here. We have fossils, isotopic analysis, plant wax, and ancient molecules. But I'm just going to be focusing on a couple of them in this lecture. these two are really important. It's the fossils and the isotopic analysis. They also go hand in hand, and you'll see a bit more about why later. So if we start with the fossils, both larger fossils like the dinosaur jaw here and tiny fossils like these foraminifera can be used. And also geographical location of all of these different fossils is really important because it can tell us what climates were like nearer the equator versus in places like Antarctica. So the first example that we're going to look at is a fossil reptile, which was found on Antarctica, and it's from the early Triassic, so around 250 million years ago. It's called Antarctonex shackletoni, so it's a little scientific name, and it's really cool because finding an animal that should be living in a warmer climate on somewhere where we know is a really cold climate, we know Antarctica to have lots of ice and snow on it, shows that, well, it can't have always been like that because this animal was living there at that point, so there mustn't have been any ice on it at the time. The continents also look pretty different than they do today back then. This is a map from of the early Triassic, or a global map, and it's not that recognizable compared to what we have now. We have a lot of tectonic movement, which has caused our continents to look pretty different. But essentially, this landmass at the bottom is Antarctica, still attached to Australia and everywhere else. And that's where this lizard was found, or this reptile was found. So yeah, that's going to have an impact on kind of what we're seeing as well, because that's how the animal could get there. The next fossils that we're going to look at are called microfossils. This just means that they are so small that they require a microscope to be seen. There are lots of different types of microfossils like pollen, teeth, microorganisms like foraminifera over here. But we're going to start with pollen fossils today. So on the right here we have some images of fossil pollen. And these were also found in Antarctica, just like that reptile. But these are identified as pollen from palm trees. So that's showing us that we have palm trees on Antarctica. And this was during the late Cretaceous, so a bit of a long time after that reptile from before. But we still don't have ice on Antarctica at this point, which is cool. This reconstruction here shows what Antarctica would have looked like, which is obviously nothing like it does today. And this is the map of what the continents would have looked like during that time as well. So we're starting to get a little bit more recognizable and similar to our modern world. But there's still some major differences. We still have Antarctica being connected to Australia, for example. So yeah. The final fossils that we're going to talk about are called foraminifera. These are single-celled organisms that have a calcium carbonate shell. The ones pictured here on this page are a type of foraminifera called planktonic foraminifera. And this just basically means that when they were alive, they lived in the water column, floating about, like just in the water, kind of like this guy here. Then the other type of foraminifera are called benthic foraminifera. And these ones are exactly the same as the other ones, except for they look a bit different, and they live on the seafloor at the bottom of the ocean. And we can use both types of foraminifera to estimate past climates by looking at the isotopic makeup of their shells. So as a bit of a recap, isotopes are atoms of the same element with the same number of protons, but a different number of neutrons. So they have a different atomic mass from each other. So here we have carbon. This is our normal carbon atom, carbon 12. So we have an atomic mass of 12, which is made up of 6 protons and 6 neutrons. And this is the more common isotope. And then we have our other isotope, the rarer one, which is carbon 13. And its makeup is 6 protons and 7 neutrons. So it has an extra neutron. We see a similar thing in oxygen as well. Where our common isotope, oxygen 16, has 8 protons and 8 neutrons, but our heavier isotope, oxygen 18, has 2 more neutrons, so we have 10 neutrons instead of 8. So if we go back to our foraminifera, their shells have carbon and oxygen in them, in this calcium carbonate here, and so we can use that to measure how much they have of each of the different isotopes. And then direct that to climate. So foraminifera are found in different layers of the ocean sediment cores. So this is one of those cores. And if the isotopic composition is measured for the foraminifera in each of the layers, then we can see how it changes through time. And we know that isotopic composition is directly related to temperature, and so we can use that to estimate changing temperatures through time. And this is the kind of plot that we get from using these isotopes. So the top line here is the global mean temperature through time, and that's looking at this axis on the left here, the y-axis. And then we also have CO2 levels recorded here as well, and that's using the axis on the right, so that's just atmospheric CO2 levels. On the bottom, we have time, so both of these are being measured through time, millions of years ago, up to 100 million years ago. And what's really nice about this is that we can pick out snapshots through time of what the climate on the planet would have looked like. So we start in the mid-Cretaceous, where we've got really, really warm climates. Then we're getting a little bit cooler, but still really warm in the early Eocene. And then once we get to the Pliocene, you can see it's a lot cooler, and also we've started to get some ice sheets on Antarctica there, and a little tiny one on Greenland too. And then the final snapshot is the last glacial maximum, and this is where we have ice sheets all coming into Europe and North America, and obviously all over Antarctica. So this is like colder than what modern day climates are like. But the great thing about this as well is that we're able to make projections of what climates are going to look like in the future. And that's what this section here is doing. So this is again just showing the CO2 levels. We're currently at around 420 parts per million. And that would be kind of the middle of this axis here, where we've got 200 years ago and 200 years ago, 200 years in the future right here. And there's three projected or predicted projections of what might happen to our CO2 levels. And that's all dependent on the actions that humans will take in the next few years. And what's great about this is that we can use this to trace back what the climates were like when the CO2 levels were similar to what they are now. So if we trace back from our 420 parts per million, we're getting to somewhere around here. But if we continue on this negative projection, the one that's going to heat up the planet the most, then we start to go further back in time to when the planet was a lot hotter, like in the early Eocene. So I've also got a little case study here. I mentioned the Paleocene-Eocene thermal maximum, or the PETM, earlier. This is a period of a major global warming, around 4 to 5 degrees temperature increase across the world. And this was around 56 million years ago. And it's marked by a huge shift in the carbon and oxygen isotope ratios from those foraminifera. And this figure here shows that exactly. So in this circle, you can see there's a huge spike kind of behind that red line in the oxygen isotope level, which is just what this means over here. And that's showing an increase in temperature. This is something that we wouldn't have seen without having these ocean cores and looking back in time at past climates. We would never have known about this event, and that's a shame, because this event is so important, because it's a period of very quick global warming, similar to what we're experiencing now. And so we can directly compare it to our current situation. We can look at biodiversity during that time, and how animals were coping with this thing, and also how the Earth recovered after it. Yeah, so stuff like this is super important, and shows us the impacts that human-made climate change might have on the world. So in summary, we know that we can use fossils and isotopes to estimate what ancient climates would have been like. This has enabled the identification of events like the PETM, which was an episode of major warming that we wouldn't have known about without isotope data from fossils. I also mentioned earlier that I was going to link a documentary at the end, and that is this right here. Um, it essentially shows a bit more about what the scientists get up to on the Geordie's resolution, and how they analyze the ocean sediment cores to work out what's going on in past climates. So if you're interested in that, or like the idea of a career in it, then I definitely recommend giving it a watch. But thank you for listening. I hope you enjoyed. Goodbye.